Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. We are talking of enrichment of uranium. Last time we looked into the gas diffusion process, which is pretty slow. And so it was obvious that something better had to be developed. And this method that was developed quite some time back is known as the gas centrifugation process. Actually, majority of uranium 235 that is obtained is usually by this technique itself. It was originally uh, discovered and developed in the former USSR, now Russia. It's again a scientific aspect, so I'll have to clarify the scientific background of it and then look into the actual process, which is very interesting, which every intelligent person must know. Uh, it deals with the concept of centrifugal force. There's a pair of forces we'll discuss sometime later, centripetal and centrifugal forces. And the basic formula for it is mv squared upon r, where m is the mass, v is the velocity, r is the radius of orbit. Um, it can be modified into what is known as mr omega squared, and then further modified into replacing omega in terms of frequency. So it becomes 4 pi squared n squared into mr, where f, of course, is the frequency. Let's keep that aside. Uh, Basically, what it means is that the amount of centrifugal force that acts or that is experienced by a body is directly proportional to the square of the frequency. So the amount of force could be very increased to a very large extent, and greater the mass, more is the tendency of the object to move outwards. This is something that we use in our day-to-day lives quite often, like the spin dryer that you have for drying clothes after using a washing machine. The drum starts spinning very rapidly, and so the force acting on the water drives the water molecules to the outer edge, and there from the sides it trickles down and is separated out. Those who are from science and remember their practicals in college know that there was a centrifugating machine to separate out the precipitate from the original liquid. And this process is also used very often in medicine, where we talk of separation of blood and plasma and platelets. Now, this is done by a centrifugating machine. Uh, Also, when milk is processed, what they tend to do is to have a centrifugating unit which separates out the clear liquid and the solid part of milk, which can then be tested or converted and so forth. So, centrifugation is a common technique, but things here in radioactivity are not all that simple. The amount of frequency that is given is of the order between 1000 to 2000 revolutions per second. So these devices are typically referred to as ultra high centrifuges. And if you work out the formula, the amount of uh, gravitational g force, as it is known, that acts, normally we have 1 g that acts on us. If you turn the system around like what I am saying, the amount of force acting on it will be equivalent to 1 million G. So if I weigh 1 kg, if I feel that I weigh 1 kg on Earth because of gravitation, in such a unit, I will weigh 1 million kilograms. So 1 kilogram becomes equivalent weight factor of 1 million times. That is the amount of force that will act on these particles. That's the principle that is used. Uh, of course, because the frequency is high, it is known as ultra high speed centrifuges, and not everybody can manufacture them because they have to be manufactured and constructed in extreme environmental conditions, vacuum systems around. You can't use normal ball bearings, so you tend to use magnetic ball bearings and evacuated systems, and even the slightest touch can completely throw the whole thing off track. So what is the structure like? There is obviously an extremely rapidly rotating drum. From the center, the gas is let in. And gas, since we are interested in uh, enriching uranium, it is going to be uranium hexafluoride, the one that we talked of last time. So it is pumped in from the middle, and the drum is spinning at extremely high speed. So naturally, as material starts getting thrown outwards, uranium 235 is slightly lighter than uranium 238. So uranium 238 starts going outwards, while uranium 235 tends to remain in the center. So it is this central enriched part of the gas that is pulled out, and the outer depleted region gas is again taken out separately, like what I told you last time. The output of the first one is given as the input of the next one. So the enriched UF6 from the first one goes as the input for the next one, and it is again spun around and again processed, and this cycle results into a very large number of such systems connected in thousands when the process was first started off. And this, I told you last time, is connecting the systems in cascades. So it's a cascade arrangement that is made, and gradually the percentage of uranium 235 containing uranium hexafluoride increases. And as this increases, the percentage increases to 2%, 3%, 5%, 7%, and so forth. The gas, if it is depleted, it may completely depleted, it is taken out separately for other purposes. Plus, please remember that we still have it only in the gaseous state. So, uranium hexafluoride, which has more of uranium 235, has been obtained in this process. This process is the one, as I told you, the most common one that is used throughout the world for enrichment of uranium. But then with time, science progresses and new ideas and new technologies come about. And so they developed now in around in this beginning of this century a technique known as laser separation. Some of these parts are still under experimental conditions. Some of them are already put to use. It uses a property of photo excitation by lasers. Lasers is light, that's why photo excite, and it excites certain molecules. That's why photo excitance excitation. The technical name for this is silex, SILEX, separation of isotopes by laser excitation. Uh, we've discussed in detail of what lasers are, so I'm not going to go into that aspect. The base material, the primary material, the feed material is again the same, which is uranium hexafluoride, again in the gas form. But it isn't taken just as it is. It is mixed with a carrier gas, and this carrier gas is an inert gas like argon or nitrogen. So what does the system and how does it work? Uh, the system consists of a chamber in which uranium hexafluoride gas is sent in the form of a jet, and it comes through and then moves out of the other opening. And from the side, it is bombarded by a laser beam. A tuned CO2 laser is used. It is tuned means its frequency can be altered. It is the frequency chosen is such that it tends to excite the uranium 235 atoms in its vibrational mode more than the uranium 238 atoms in, of course, uranium hexafluoride. What this process does is it prevents or suppresses the tendency of uranium 235 to condense as compared to uranium 238, which is slightly heavier. And so in the vapor state, it tends to remain in the outermost layer of the jet, while the central layer has more of uranium 238 containing, uh, of course, in UF6. So the central jet is separated out and the outer jet part circumference is pushed out and collected separate. This is the enriched form. And this process, of course, is repeated a few times or a multiple number of times till the enrichment level reaches the desired stage. The movement of uranium 235 atoms is higher than those of uranium 238, so this separation process becomes easy to manage. And this original process was first developed by a private company in Australia. But nowadays, of course, um, nuclear non-proliferation and all those conditions, and all these big countries don't want these new, advanced, and cheap technologies to fall in the hands of others who can enrich uranium as they want. So there are a lot of restrictions on this technology, control by a few to take advantage of so many things. Let's keep that aspect separate. There is one more technique that is simultaneously being talked of and developed. It is known as MLIS, molecular laser isotope separation. In this, an infrared laser beam is used of 16 micrometer wavelength. We have talked of what all these terms are. Um, what it does is it excites uranium 235 molecules more than U238 into the process of dissociation. See, what has happened is uranium 235 and 238 have associated themselves with fluorine. Now, this because of this laser beam, this binding is slightly separated out. And what happens is uranium 235, instead of getting remaining as uranium hexafluoride, becomes uranium 235 pentafluoride. And since it is structurally different, it tends to get crystallized out much faster and separated out much better than the uranium 238 part. And that's how this processing results into separation. So laser beam helps 235 to dissociate into pentafluoride rather than hexafluoride, and then separation is possible. Now the next step, obviously all this whichever process, all the three of them, diffusion or centrifugation or laser techniques, what you have is enriched uranium 235 hexafluoride or pentafluoride in the last possible case. This is then reduced down again, and pure uranium is obtained, in which the percentage of uranium 235 is higher and higher and higher as desired. Depending upon the type of application, the percentage of uranium 235 is suitably increased. In the remaining part, there is the uranium 235 has been negligibly reduced. So this is known as depleted uranium. And this depleted uranium also has its own uses. Since it's a heavy metal, it is used as radiation shielding. Uh, it is also used to produce armor piercing weapons in tanks and other and ships, etc. And there is one more process uh, in which there is a blanket of this depleted uranium that is used and produced. Not a normal blanket that we talk of, but a very special one. And I'll talk of that application much later when we talk of special reactors, breeder reactors, and so forth. Uh, so that's what happens to the depleted part. But what about the enriched part? Depending upon the percentage of concentration, the applications and the names are also looked into. Whenever the percentage is less than 20%, it is known as LEU or low enriched uranium. If it is less than 2%, it is known as slightly enriched uranium. Um, if it is a low enriched uranium and it is between 3 to 5% of enriched uranium, it is used in most of the light water reactors, LWR, something that I will talk of next time. So light water reactors tend to use only 3 to 5% of enriched uranium. If it is between 12 to about 19.75, these are special reactors used for research purposes. Their output patterns are different. And anytime the percentage goes beyond 20, it is said to be HEU, that is highly enriched uranium. And as I told you last time, the percentage can, by various techniques, can be increased right up to 97%. Out of that, the time when you cross 85% of uranium 235, what you get is weapons grade uranium. And it is this weapons grade uranium that is used in all the nuclear devices that are used. Uh, there is, of course, a special type of a nuclear device known as the implosion device. You must recollect that the Pokhran explosion was an implosion device. Uh, there, because of the special design of the bomb, it is possible to use uranium that has been enriched even slightly lower than 20%, and that is good enough. So that's how we have a variety of applications of enriched uranium. Um, but can I use this directly into a reactor? No. There is one more step, and that is converting this uranium 235 that has been enriched into a suitable form to be utilized in reactors. And that is going to be our next step. Uh, if you have liked whatever I have said, um, please like and subscribe to this channel. Uh, if you have the notification on, you'll know when I'm going to talk of the next topic related in this particular context. Um, we will have to talk of not only the fuel form, but also what nuclear reactors are, what are their different types, and how they are put to use. Till we discuss all that, Prakash Zog says, Namaskar.